Hello community, here we go again. Parametric UMAP dimensional reduction. This is the edition where we tune our Ferrari and we add some turbo. So here we go. The turbo, of course, will be our autoencoder. But let's start at the beginning. We want to have some parametric UMAP with our specific defined neural network. So at first, some installment, we have to install some library. I decided to upgrade my PyNN descent, finding the nearest neighbor. And then I did an upgrade also from the TensorFlow probability. And I had to upgrade the Shim package. And then we had to install NumPy, SciPy, Panda, scikit-learn, datashader, HoloViews. And since everything is now running on Number, we have to do the number thing. And finally, then we are able to pip install our UMAP learn library, the Python library, with the plot functionality also added for us, so we just can go and plot the loss function, because this is what we're interested in, to see the performance of the system. So here we go. At first step, we load our data. It is the MNIST dataset. We have 70,000 black and white pictures of our digits handwritten from 0 to 9. We have 28 pixels times 28 pixels. And this is our training data set. To speed up the training and to find out for myself, I do a little experiment. I reduce the number of training images from 60,000 to 10,000, so reduce dramatically the training data set, and the validation data or the test data images from, I think, 10,000 to 5,000, so I half even for the validation. And then comes the beautiful part. We have now the option to define our encoder neural network. Since we are going here in the vision sectors, we have pictures 28 pixels times 28 pixels. We go, of course, with the typical convolutional neural network architecture. You notice, please, if you have a specific task, insert here your specific neural network, whatever it is. If you can code it in Keras, in TensorFlow 2 and Keras, if it's a sequential model, beautiful. Do it, optimize your encoding from your high-dimensional input data space where you have your data cloud. So the encoder does the encoding to the embedded space, to the low-dimensional embedding, where we have also the structure of our graph preserved. The closeness relation between our data points are there. And we have a similarity of our graph structure, the information encoded in our graph structure. So this is the encoder. And of course, we do the decoder. Yes, because we want to really fine-tune our model. This should be a Ferrari and not a Volkswagen. So therefore, we also do the decoder neural network. You have it here. All credits go to Leland McInnes and his team. They are the inventor, the creator of UMAP, and his team also did here the coding for the parametric UMAP. So all credits go to them. I leave you the link to the original archive, to the preprint paper, and to the code sequences where I took this code to show you. We have here our next model for the decoder, our number of parameters. Told you about the convolutional network. You have the convolution layers, the pooling layers, don't forget the fully connected layers, everything defined. And here we go. We now import our parametric UMAP. Remember, it's a subclass of UMAP. You have it in your UMAP library. This is great, already there for you. And then when we do the parameters, I told you in the Fast and Furious version, we just defined the number of training epochs. And this was it. Yeah, verbose is true. These were our own two parameters that we had. But now we can play a little bit and I show you how beautiful the performance of this system can be if we fine-tune it a little bit. So we define our encoder network and we have a very particular decoder network going back to the original data space. The number of training epochs is limited because I don't want to use here the Colab GPU. Just for demonstration, filming purposes for a YouTube video when somebody needs the CPU resources, maybe for his academic whatever. number of components defined. Now we say the parametric reconstruction is true. Up until now we said no, it is do not do the reconstruction from the embedded space back to the original data space to the vector space, because this would be too complicated. But now look how easy it is. You just do the Boolean value set to true and you have your parametric reconstruction done for you. And of course the real turbo engine here that we activate is now our autoencoder, and we say yes, true. We want to have our autoencoder. We want to have additional terms in our loss function. You remember the cross entropy, and when we optimize the cost function. And of course, for the reconstruction validation, we have our test images. Remember, I also reduced here the dataset availability to about 5,000 pictures of 28 pixels times 28 pixels in black and white. Jesus. Okay, this is done. We get a warning, TensorFlow probability not installed. TensorFlow probability not installed setting. What do you mean TensorFlow probability is not installed? This is why I did it. TensorFlow probability, TensorFlow install. Oh, wait, there's something missing. Okay, interesting. Never had this before. Okay. Maybe there is some problem. What is gonna tell us? Wait. Setting global correction loss weight to 0. Yeah, beautiful. Okay, yeah, no problem at all. This is, if you remember, if you look at the complete list of parameters in Parametric UMAP, the class, or I think it's a subclass, you see that we have also their parameter for the global correlation loss weight. I think in default it is 1, and now it's 0. Yeah, okay. Never mind. And here is the action gonna happen. We trained our model. We have a fit transform on the train images of our embedder, and our embedder is here our defined encoder and decoder neural network functionalities. Beautiful. We have, of course, rather than the autoencoder loss is true. The decoder, yes, we have defined. We do remember it is exactly the same in the parametric UMAP to the classical UMAP. Step 1 is the same. You construct the fuzzy simplicial set. This means more or less we construct a graph from our in our high-dimensional topological space. From our high-dimensional vector space, we find the nearest neighbors. We build a forest with 10 trees, 13 iteration, exiting after 4 iteration. We are finished with the nearest neighbor search. Beautiful. And we construct, or the GPU is now doing the embedding. Great. The expected time of arrival is 8 minutes. We are in epoch number, 30? Wow. Oh yeah, of course. Heaven's sake. Wow, this is gonna take... No. This is too long. This is too long for demonstration purposes. Jesus, come on. 2 of 30, and it takes about 8 minutes. No. So you can imagine that we have done this. How can I further reduce it? I don't think anywhere at all. I can reduce maybe our convolutional network. Yeah, but I need it. Oh, come on. Come on. Okay, as you can see, it takes quite some time if you have more complex, if you have both neural networks, the encoder and the decoder, a little bit more specific to the task. You need time. You need 7 minutes, 10 minutes per epoch. So yeah, okay. Okay, should I wait? Should we go? Should we wait? Should we go? Okay, I tell you something. I make here a version that we just go on as it would be, and maybe afterwards I just put it on pause and I see if I can show you in some hours the result. If I'm allowed to log up a free Colab GPU just for demonstration purposes, yeah, let's do this. So what we do, we want to have, of course, we want to plot the loss function. Well, and if we have the embedder, you can see here, we just want to plot it. And of course, we want to see the cross entropy going down if the number of epochs increases. This is everything we want to see. This is the code how you can do it. As I told you, every credits go back to Leland McInnes and his team. And this is just now a matter of waiting or not waiting. Yeah. Okay, so this was it. Parametric UMAP, MNIST embedding with a convolutional network and with an autoencoder loss, additional loss function. This is beauty. This is really something gorgeous. If you do this, you have really understood Parametric UMAP. You know now how to use this beautiful dimensional reduction mechanism, this algorithm, and I hope you will apply it successfully in your work. I say thank you, and I see you in the next video.